will discuss multivariate probability density functions. So, after completion of the multivariate distribution functions we discussed, and also we discussed multivariate probability mass function and their properties, how to find the probability mass functions. So, here also we will learn how to find the how we can define a joint probability density function for a multivariate random variables. So, now you can remember that when we discussed this when we discussed this bivariate random variable, bivariate continuous random variable. So, in that case, so we consider that, so we consider two random variables x1 and x2, and in that case we discussed this is the cumulative distribution function, probability that x1 is less than equal to x1 comma x2 is less than equal to x2. So, this is the cumulative distribution function, and for bivariate random variable, continuous bivariate random variable, we assume that this is differentiable. So, with respect to x1 and x2, so that there is a function, we assume that there is a function x1 and x2 such that this can be represented as like in this way. So, minus infinity to x1 minus infinity to x2. So, then we need to change this variable as we are using x1 x2 as the limit. So, this maybe we can write as a u and v du dv. So, then this can be represented as f of x1 x2 x1 x2. So, this is the cumulative distribution function, and this function it is known as the density function. So, this density function can be found x1 x2 x1 and x2, this is nothing but del x1 del x2 f of x1 x2 x1 x2, assuming that this exists for all x1 x2. Similarly, when we are extending for multivariate random variable up to n random variable x1 x2 xn, then we consider x as a vector, x1 x2 xn is random variable, xi is a measurable function from S to R. So, that x this vector, it is random vector, it is a function from S to Rn. So, basically this is nothing but these things, and so x defined by x of s is nothing but this is x1s, x2s, xns. So, this is a element in Rn. So, whenever all these random variable are continuous random variable, then this random vector it is known as multivariate continuous random variable, and in the multivariate continuous random variable we assume that there is a function. So, similarly just it is extant, and distribution function we have already discussed f of x1 x2 xn x1 x2 xn, this is not this is equal to probability that x1 is less than equal to x1, x2 is less than equal to x2, xn is less than equal to xn, and this is can be whenever it is a continuous random variable, there exists a function f of x1 x2 xn, small f of x1 x2 xn, such that this can be represented as minus infinity to x1. So, this is minus infinity to xn minus 1 minus infinity to xn. So, f of x1 x2 xn, f of x1 x2 xn, then this is you can write some variable u1 u2 un, and then du1 du2 dun, and this function it is known as the probability joint probability density function. So, this joint probability density function it is represented by f of x1 x2 xn, f of x1 x2 xn, this is nothing but this is equal to del n del x1 del x2 del xn, and we can represent that as this is f of x1 x2 xn, derivative of this we assume this exists, and this function is this value. So, similar to the univariate cases and bivariate cases, this invariate cases also this function we have some of the properties. So, this property is written here, and you can see that this is represented, this multivariate probability density function it is given here. So, which is joint probability density function of a n-variate random variable is given by this, and the joint cumulative distribution function can be represented as f of x1 x2 xn is in this way. So, yeah, so this we have already discussed. Now, next we will discuss the properties of properties and the marginal probability density function. How we can find the marginal probability density function from the joint probability density function. So, some of the properties are similar to the cases when it is for univariate cases and also bivariate cases extension. It is just a just straightforward extension to the multivariate cases. So, let us discuss some of the properties. So, here this cumulative distribution function, it is non-decreasing. If you fix some of the coordinates and one coordinate you increase. So, we have discussed that. Suppose x1 x2 xn, similar to the bivariate cases, suppose x1 then x2 xn, and suppose this is one value variable, one of the variable, suppose this is the vector 1, we are denoting by x1 x2 xn, and this is 1 1 1, and also this another vector we take, suppose other coordinate fixed, suppose this is x2 fixed as it is same, then xn also fixed as it is, and the x1 variable this changed. So, such that x1 1 is less than x2 x1 2. So, x1 2 this coordinate. So, in that case we can write this less than equal to f of x1 x2 xn, and then x1 of 2, and this function is same, these values are same because we are just fixing other coordinates. So, coordinate wise actually we can say that it is a, because in Rn this we cannot order. So, we do not have proper order. So, if we fix some of the coordinates, then it is just a order between this one value, that is r in the R. So, there is a order. So, we can say x1 less than x2, if it satisfies, then f of x1 x2 xn, this will be less than equal to this value. So, this is non-decreasing in every coordinate. So, in that case this derivative also, partial derivative of every values variable, it will be greater than equal to 0. So, in that case we can we have this x1 x2 xn, this x1 x2 xn, this is nothing but this derivative with respect to del x1 del x2 del xn, and then this is f of x1 x2 xn and x1 x2 xn. So, this will be greater than equal to 0. This is one property. Another property, as usual like bivariate cases we discussed. So, another property is that minus infinity to, so if you take the integration over whole Rn minus infinity to plus infinity and of this probability density function, it is nothing but the probability of the certain event. So, x1 x2 xn, so dx1 dx2 dxn, this should be is equal to 1. So, these are the some of the properties, and also many other properties like R2 we have discussed. So, these are all the extension similar properties we so for example, suppose if you want to find, suppose you have 2 points like A1 A2 An, and one point is like this, and another point is B is B1 B2 Bn. So, we write in a transpose, it is a vector. So, like this column. So, then if you and also we have this ai is less than equal to bi for I is equal to 1 to n. So, in that case how we, what is the probability, if we ask that what is the probability that x1 is taking value greater than a1 less than is equal to b1, x2 is this taking value greater than equal to a2 less than equal to b2, then this an this value an is less than xn less than equal to bn. This probability we can find by just integration, like this will be a1 to b1 like this. So, n minus 1 to bn minus 1 an to bn, this with respect to this probability density function f of x1 x2 xn, then x1 x2 xn, then dx1 dx1 dx2 dxn. So, in this way we can find the probability in a rectangle. Here actually it is n dimensional some cube in 3 dimension. So, so it is n dimensional So we can represent in the graphically we can represent, but in the two dimensional cases it will be nothing but it is like a square like this. So this is like A1 to B1 and this is A2 to B2 like this. So this probability inside this region in the bivariate case we have discussed. So these are some of the properties. Now next we will discuss how we can find the marginal probability density function if you know the joint probability density function. Suppose we know the joint probability density function, so that means we know f of x1 x2 xn and x1 x2 xn, this function we know for a multivariate random variable xn x. So this vector, so this is we represent by this vector x1 x2 xn. So then this joint probability density function, so joint probability density function we know for all x1. So let us discuss that. We know that this function, we know this function, this value x1 x2 for all x. So this is x1 x2 xn belongs to Rn. So we know this value. So now we have to find the one of the variable or any subset of the variable if you consider. Suppose there are n vectors, so any subset means it will be if you don't consider null set, then it will be 2 to the power n minus 1 number of subsets are there. So one of the subset may be x1 can be taken as a one random variable, x2 like xn. If you consider 2 at a time, so x1 x2 another random variable, like x2 x3 another random variable. So in this way, so many subset of the random variable. So any subset of the random variable, suppose we want to find the cumulative distribution function or probability density function, or in this case probability mass function. So then we say that marginal, so marginals. So here we will find the marginal probability density function. So for example, suppose we want to find the marginal density function of x1. So how we can find? So you can remember that for the bivariate random variable cases, how we did that. So bivariate random variable cases, we just integrate the other variable. So f of x1 x2 xn. So we do, so then f of x1 will be nothing but if you take the integration minus infinity to plus infinity, minus infinity to plus infinity, here we have to do integration because we want to keep this x1. So we will keep x1. So then x2 x3 xn will integrate dx2 dx3 dx2 dx3 dxn. So if you do this, so then you will get the marginal probability density function of x1. So similarly, if you want to find the marginal probability density function of x1 x2, so then we have to do the integration of the other variables. So this is minus infinity to plus infinity, minus infinity to plus infinity, minus infinity to plus infinity. So this is the joint probability density function. It is known to us for any value x1 x2 xn. Then we will do the integration from x3 dx3 dx4 like dxn. So x1 x2 will not do, so will not do. So this is integration we have to do the remaining variable. So now similarly any values, so if you want to do, we want to find this suppose x1 x2. So instead of x1 x2, suppose we want to find the marginal probability density function of x2 x3 then xn. So this is one subset. So then x2 x3 xn. So we want to keep this variable. So these random variable we are interested to find the marginal probability density function. So in that case how we will do, because here this x1 we don't want, so we will do minus infinity to plus infinity this joint probability density function x1 x2 xn, x1 x2 xn, so dx1. So this, so whatever we don't want, we will do the integration. So then we will find the marginal probability density function. So this is the concept we have. I hope you have understood that how to find the marginal probability density function if you know the joint probability density function. So it is discussed here. So here you can see that it is they have found in that in this slide it is given y1 y2 yn minus 1. Actually it is this variable, it is used y1 y2 yn minus 1. This is just a variable only. So then because we want to keep those variables, so we need to, because yn we don't want, so that's why we integrate this with respect to dyn. So, similarly here we have already discussed we want to keep y1, but we do not want to keep the other variable. So, then we integrated y1 to yn. So, all this we have integrated. So, we did the integration. So, this is the concept of joint probability density function and the joint and their properties, and how to find the marginal probability density function from the joint probability density function. Now, we will discuss how a multivariate random variable we can say they are independent random variables. So, it is very important concept because this is actually we frequently use in our future topics like whenever we learn statistical inference. So, when we define the random sample, we say that these random variable are independent and identically distributed random variable we say. So, what does it mean? So, independent random variable means what? So, in case of discrete case and in case of continuous case we will discuss. So, here actually this y1, y2, yn are the random variables it is given. So, let us use the same notations also. So, let y, so y is the vector y, y1, y2, yn. So, let y is equal to y1, y2, yn be a random variable, let be a discrete random variable, suppose discrete random variable. So, discrete random variable we have discussed. So, then we discrete random variable with probability mass function, joint probability mass function, I am just writing the abbreviation PMF, joint probability mass function of y is P of y. So, this tilde whenever we write it is like a vector. So, this is I am again explicitly writing y1, y2, yn, then y1, y2, yn. So, this is nothing but we already discussed, this is probability that y1 taking small y1 is the real number, some value, y2 taking this probability y2, and capital Yn taking this small yn. So, this is the probability that y1 taking small yn, y2 taking small y2, yn taking small yn. So, then with joint probability mass function of y is given by this, and the marginal probability mass function of yi is P of yi. So, this is yi. So, this is nothing, this is actually defined as P of yi is equal to small yi. So, this is the probability mass function of just yi. So, for I is equal to 1 to n. So, this is the marginal probability mass function of yi. So, then what will be the when we will say that y1, y2, yn are independent random variables. So, you can remember that how independent concept we discussed. So, for two events we say independent means A intersection B is nothing probability A into probability of B, then we say that two events are independent. For whenever it is a random variable, the concept is different. So, it is this independence is defined with respect to, if it is discrete then with respect to probability mass function, and continuous with respect to probability density function or cumulative distribution function also we can have definitions for independence. So, now for two random variables you can remember that we say they are independent if their joint probability mass function can be represented as their marginal probability mass function, product of their marginal probability mass function for all, here it is important, for all y1, y2 belongs to real number, because y1, y2 are real number. So, here also we discuss this similarly, this is the extension, the random variable, random variables y1, y2, yn are said to be independent random variables if probability joint probability mass function, so that is P of y1, y2, yn, y1, y2, yn joint probability mass function can be represented as their product I is equal to 1 to n P of. So, we can, instead of writing as a this kind of notation, let us write very simple way P of y1 product of P of y2 P of yn. So, note that here for all, either we can write for all y, this is y1, y2, yn belongs to Rn for all y. So, this can be represented as a very simplified notation P of y, this is equal to product I is equal to 1 to n P of yi. So, basically same expression I am representing in a simplified notation only, and this is we can write for all y1 or all I, for all y belongs to R for I is equal to 1 to n. So, basically same things we have written here in a different notations only. So, it is said that the y1, y2 independent random variable means we understand the joint probability mass function can be represented the product of their marginals. So, similar to this, so let us suppose on example that how we can find a joint probability mass function. So, because if they are not independent, so we may not know that what is the joint probability mass function if it is not given to us. If marginals are known, for example, if you consider a Poisson random variable, we have discussed that. So, let yi has a, let y be a Poisson random variable, with parameter lambda I for I is equal to 1 to n. So, note that lambda I are different. So, yi not identically distributed random. Identically means that they have same distributions. If we say suppose they are parameter with lambda, so then they have same distributions for all y1 also having Poisson distribution with parameter lambda, y2 also having Poisson distribution with parameter lambda. So, then we say that they are identically distributed random variable. But now here we are considering not identically distributed random variable. Suppose yi be a Poisson random variate with parameter variable with parameter lambda I for I is equal to 1 to n. Now, if they are independent, so then we can find their joint probability mass function. So, what is the joint probability mass function? So, the joint probability mass function of yi, first we let us find out the probability mass function of yi. Hence, because it is a Poisson random variate, the probability mass function of yi is given by P of yi. So, this is nothing but it is equal to yi is equal to yi. So, we know that we have already discussed Poisson random variate e to the power of minus lambda I to the power of yi by yi factorial. Whenever y is a real number, so this can take 0, 1, 2 and this is 0 otherwise. Basically, it is not only real number, it is a integers, it is taking only integer values. The range of these random variables are 0, 1, 2 like this, 1, 2, 3 like this. Now, if y1, y2, yn are independent random variables, so basically here we are assuming that they are independent random variables. If it is not independent random variables, then we cannot find their joint probability mass function in this way, because here with this assumption that they are independent random variables, we can find the, if y1, y2, yn are independent random variables, the joint probability mass function of this vector y1, y2, yn is given by, so if they are independent random variables, so then we can joint probability mass function is given by y of y. This is equal to just I am again explicitly writing this notation y1, y2, yn. So by definition, if they are independent random variables, so then it is the definition the equivalent that it is, we can write their product y1, y1 for all y1, y2, y3, yn. So we can write p of yn, yn. So this is equal to e to the power of minus lambda 1 to the power of y1 by y1 factorial, e to the power of minus lambda 2 to the power y2 by y2 factorial, like this, e to the power of minus lambda n to the power yn by yn factorial. So by this, if you put y1, y2 as I is equal to 1 to n, so then we can find this probability density function. So the joint probability density function can be, so this is for whenever each YIR between 0 to 1. So we can write, just let us simplify it. So this is equal to e to the power of minus summation of lambda I, and then lambda 1, so product of lambda I, or we can say to the power yi, and by product of I is equal to 1 to n, this is into yi factorial. So if it is integer, so if this is yi is equal to 0, 1, 2 like this, for I is equal to 1, 2 like this, 1 to n. So otherwise this is 0. So you will write the like this. So let us write again. So p of y, this is equal to, so just what we have simplified here, we will write here e to the power of minus summation of lambda I, then product of I is equal to 1 to n lambda I to the power of yi by product of I is equal to 1 to n, then product of yi factorial, if for yi is equal to 0, 1, 2 like this, for I is equal to 1 to n, and this is 0 otherwise. So this is 0 otherwise. So this is the joint probability mass function. So this is one concept we understood, that if we know that these random variable are independent, then we can find their joint probability density function, joint probability mass function, if we know their marginal probability mass function. So this is the joint probability mass function of a independent Poisson random variables, the y1, y2, yn, that discussed. So hopefully you have understood it. Next we will discuss the continuous cases. So when these random variable are continuous random variable, how we can discuss that they are independent. So we have to discuss with respect to their probability density function.